Okay, here we go with section 10.4, adding, subtracting, and multiplying radical expressions. So we're going to start with to add or subtract radical expressions. What do we do? Well, the rules that you don't do are if you have the square root of a plus b, you cannot separate it into the square root of a plus the square root of b, and the same for if you have the square root of a minus b, you cannot separate it into the square root of a minus the square root of b. It does not work like multiplication and division. So keep that in mind first off. Now, like radicals are radicals with the same index. That means that if one's a square root, the other has to be a square root, and the same radicand, which means that if it's the square root of 3, then the other radical is also the square root of 3. Like radicals can also be combined with addition or subtraction by using the distributive property. So for example, if we look at example A, we have the square root of 3 plus 7 square root of 3. If you notice here, their index and radicand are the same. So therefore, you basically treat them as if they're variables. So as if it was an x. If there's no number there, we're gonna just add a 1. And so you're asking, what is 1 square root of 3 plus 7 square root of 3, which makes 8 square root of 3. Okay, so we're going to try it again. Now we have 10 square root of 2 minus 4 square root of 2. I have exact same radicals. So therefore, I'm just focused on the numbers on the outside. So I have 10, minus 4. 10 minus 4 is 6. So my solution would be 6 square root of 2. Again, you want to kind of think of it as if it said 10x minus 6, 10x, trying to erase that, minus 4x, and you tell me it's 6x, right? I don't know why we're doing that. Sorry. Here we have square root of 5 plus square root of 3. Well, I may have the same index, but my radicands are different. So therefore, it cannot be simplified. Okay? Now we are going to look at D. We have the square root of 2 plus 4 times the cube root of 2. This time we have the same radicand, but our index is different. Our indexes are different. So therefore, it still cannot be simplified. So I hope you see the difference when I can add or subtract versus when I cannot add or subtract. So here we go. You want to make sure that your radical is in its simplest form before you add and subtract. So I want to make sure that square root of 27 and the square root of 75 are in their simplest radical form. So square root of 27 and square root of 75, if I think of perfect squares that go into 27, 9 is one. And if I think of a perfect square that goes into 75, 25 is the other. So I can take the square root of 9 and I can take the square root of 25. And they're going to simplify to become 3 square root of 3 and 5 square root of 3. Now, because my index and my radicand are the same, I'm just going to add 3 plus 5, which gives me 8 square root of 3. Ta-da! Next, we have 3 square root of 20 minus 7 square root of 45. Again, we want to make sure that our radicals are simplified. So if I have the square root of 20 and the square root of 45, and 20, the perfect square that goes into 20 is 4, and that breaks down to become 4 times 5. The perfect square that goes into 45 is 9, and that breaks down to be 9 times 5. So we have 3 times the square root of 4 times 5 minus 7 times the square root of 9 times 5. We know that the multiplication rules of radicals means that they can separate. So I can take the square root of 4 and I can take the square root of 9, and that leaves me with 3 times 2 square root of 5 minus 7 times 3 square root of 5. 3 times 2 is 6, 7 times 3 is 21. Now my index and my radicand are the same, so all I'm going to do is focus on those outside numbers, which are 6 and negative 21. So 6 minus 21 leaves me with a negative 15 square root of 5. Oh, let's see what happens when there are 3 terms. So I'm going to again simplify all 3 terms if they are not already simplified. So 75, what's the largest perfect square that can go into 75? Well, that would be 25. 25 times 3 makes 75. What is the largest perfect square that could go into 12? That would be 4. 4 times 3. So I'm going to write them in factor form. I'm going to use the multiplication rule and separate them. And I'm going to take the square root of 25 and take the square root of 4, which leaves me with negative 5 square root of 3 plus 2 square root of 3 minus 3 square root of 3. And again, we're just focused on the outside numbers. So I have negative 5 plus 2, and negative 5 plus 2 is negative 3 minus 3, and that gives me negative 6 square root of 3. Okay, well, what happens when there are variables involved? Well, same thing. You want to get it down to its simplest radical form. So when I look at 45x to the third, I want to think of what is the largest perfect square that goes into 45, and I want to think of how can I separate x to the cube between having a an even exponent and a odd exponent of 1. Oh, exponent of 1, basically. So it becomes the square root of 9x squared times 5x plus x times the square root of 5x. The reason why the 5 and the x are together is because they're not going to be broken apart. They're basically primes in a sense. Well, 5 is a prime and x is a singular variable. So let's keep going. Well, 9x squared, we're going to separate it. And 9x squared, the square root of 9 is 3, and the square root of x squared is x. So we pull that out. We're going to simplify 3 times 3x, and that gives us 9x. Now my radicals are the same, so I'm going to focus on the outside. And I have 9x plus x, and that makes 10x square root of 5x. Okay, so we're going to simplify this radical expression. Notice how 9 is not a radical. It's just a number, so we're not going to change 9 or affect 9. But we're going to find the cube root of 64 and the cube root of 14. So here we go. So the cube root of 64 is 4. And the cube root of 14 is just cube root of 14. 14 is only 2 times 7. And 2 and 7 are both prime numbers. Okay, notice how there are no more radicals, but I still have like terms. I have 4 and negative 9. So I can combine 4 and negative 9, and that makes negative 5 plus the cube root of 14. And you are done. Can't go any further, can't simplify any more than that. So that is your answer. What happens when we subtract? Oh no, variables in the denominator. Well, not variables, numbers. What happens is that you have to have a common denominator. So if my denominator are not the same, I need to make them the same. So I have a lot of things to focus on here. I have to focus on having the same denominator, having the same radical. Oh my. But it is all doable because they're all skills you already have. So let's start off with the radical. So the square root of 45 breaks down to be the 3 times the square root of 5. Why, do you ask? Because if I have the square root of 45, the largest perfect square that goes into there is the square root of 9, and I'm left with the square root of 5. Square root of 9 is 3, and I bring down the square root of 5. So the square root of 45 is 3 square root of 5. So, continue. Now we're going to worry about having the common denominator. What is the least common multiple between 4 and 3? Well, that would be my LCM. Well, not M. We're talking about denominator, so we're going to write LCD. So my L, I probably should turn on the bed. My LCD would be 12. So I asked myself, how does 4 become 12? And I'm going to have to multiply by 3. What I do to the denominator, I have to do to the numerator. How does 3 become 12? I multiply by 4. What I do to the denominator, I have to do to the numerator. So, now I'm here, and now I'm going to simplify. So 3 times 3 is 9, 4 times 3 is 12. 4 times the square root of 5 is just 4 square root of 5, and 3 times 4 is 12. Now that I have the common denominator, I'm just going to focus on my numerator. And my numerator says 9 square root of 5 minus 4 square root of 5, and that makes 5 square root of 5 over 12. Ta-da! Okay, next we're going to talk about multiplying radical expressions. So we're going to use our distribution property, and remember I call this the over property. Everyone gets what's on the outside. So we have the square root of 3, and we're going to distribute it. That means we're going to multiply square root of 3 to each term on the inside. So I have square root of 3 times square root of 3 minus square root of 3 times square root of 2. Using our multiplication rule, that means that they can be combined under the same radical. So I have the square root of 3 times square root of 3 is square root of 9, which is 3. Square root of 3 times square root of 2 is square root of 6. They're not like terms, so there's nothing else I can do. So boom, I'm done. Alright, what happens when I go from multiplying a monomial, well, two binomials with radicals in them. And I'm like, oh mom, what am I going to do? Well, we're going to use FOIL. So in this case, when we use FOIL, we're going to distribute. So here's your first two terms. That's your F, remember? And we're going to multiply our outside terms, our O, our inside terms, our I, and our last two terms in our binomials are L. We're going to FOIL. So we have, what we end up with is the square root of 3 squared minus 8 squared. What's the beauty of this is that if we use our rules or our shortcuts from 307, we could go straight to this, but the hope is that once we FOIL, we have square root of 3 squared, and then we have minus 8 square root of 3 plus 8 square root of 3, and then we have minus 8 squared because a negative and a positive. Our middle two terms cancel out, so we're left with the square root of 3 squared minus 8 squared, and that equals 3 minus 64. 3 minus 64 is negative 61. So what happens here? I have a whole lot going on. I have addition underneath my radical, and I have a binomial. So what does this turn into? Well, a whole lot of fun for you. That's what it turns into. No, I'm kidding. So what we're going to do is remember from 307, our sum, I can't talk, our perfect squares rule. And so the rule is if I have I'm trying to write I promise my pen and I are not getting along. I'm writing A repeated. A, did the pen go off? It's still on. A, let's try another pen. Maybe that's the problem. A, okay. A plus B squared. I promise I don't write this horrible. I think it's my pen that I'm using on the screen, and it's not allowing me to write pretty at all. It equals A squared plus 2 times A times B plus B squared. Oh, that looks so horrible, but that's what it is. So for this, in this case, our A term is the square root of A plus 1, and our B term is the 2. So now we're going to plug it into the rule. So when we plug it into the rule, we end up with the square root of x plus 1 squared plus 2 times the square root of x plus 1 times 2, that's my b, plus 2 squared. And so that's how we got to this point, or why we jumped straight to that point. Could we have done FOIL? Yeah, but it would have been a little messy and a lot of work. So not a lot of work, just cluttery. That's not a word, but go with it. Here we go. So keep going. I'm going to clean this up, and 2 times 2 is 4. Now I'm going to combine my like terms. Notice my only like terms are plus 1 and plus 4. So when I combine plus 1 and plus 4, I get 5. And there are no more like terms, so that means I am done.